Hello, stats class. Here's lesson 9.1c on significance tests and errors, because what we're doing with these significance tests is we're making a decision about the truth of the null hypothesis. Which is also called H0. And the thing with making that decision to reject or not reject is sometimes we are wrong, even if we did everything right. There's a saying that says statistics means never having to say you're certain. We're almost certain that this is true, but not quite. So I have an analogy that really helps to understand this, and we're going to talk about law and jury trials for just a bit, and we're going to compare them to significance tests. And we're going to make a table for each one. So we're going to leave some room to write in this table. There are 4 options, and we need a little bit of space for each one. And then we're going to do the same 4 options over here and compare and contrast. So if with a jury trial, the truth, which is what we're hopefully trying to find, is that the person on trial is either innocent or guilty. And we would like to find that truth. So the jury debates over the evidence and they come to a decision. And they never say the person's innocent. Have you noticed that? Even if the truth is they're really innocent of this particular crime, but they're guilty of other things, of course. So they would not say innocent. They would say not guilty. Or they would say guilty. Those are the 2 decisions that they might make. Now, 2 of these boxes represent correct decisions. If the person didn't do the crime and they're found not guilty, that's good. That means, yay, they made their correct decision. That's a smiley face. I draw weird smiley faces with their mouths open because that's how most people I know smile, so I hope you don't mind. Then the other correct decision is if the person is guilty and the jury finds them guilty. That's also correct. We would hope that most of the time it's going to be in one of those spaces. So let's think about the other 2. There's 2 things that could happen that would be wrong decisions. And one of them is if the person is innocent of the crime, but the evidence points to them so strongly that the jury finds them guilty. And that's a bad thing. It means an innocent person goes to jail. And that's bad. It's bad for a number of reasons. First of all, for the innocent person, but also because the real guilty person is still out there somewhere, and that really bothers me. But so that is a bad decision, but they wouldn't have known it. They thought that the person was guilty. And then the other thing is sometimes the person's really guilty, but they call them not guilty, and that's because they, actually, let me finish writing this first. That means that the guilty person goes free, gets away with their crime, and possibly commits another crime later. That's also bad. So 2 possible errors that a jury could make. This error comes from not having enough evidence. Like maybe they have some evidence, that's why they're on trial. And this is maybe they're just interpreting the evidence wrong. So anyway, 2 things that could go wrong. If you've ever seen the movie 12 Angry Men, or it's also a play, Cascade put it on several years ago, and I loved the fact that somebody from Stats was in that play. They spend the whole time, the whole entire movie or play is the jury debating over this murder trial. And the idea comes up of what if we're wrong? We can't just decide quickly without thinking about it that they're guilty, because we don't want them to go to jail if they're not really guilty. And we can't make this decision too quickly either, because then they might go free when they're really guilty. We're really trying to avoid these two situations and do these two. So you should watch that movie sometime. It's really good. Significance tests have the same basic idea. The truth is either the null hypothesis is true or the null hypothesis is false. It's kind of like that null hypothesis is our defendant or our person who's on trial, and we're trying to decide based on the evidence that we have to make a decision about not rejecting it. We never say accept, just like we never say innocent, we say not guilty. So it's a don't reject would be the equivalent of not guilty. Or if we think that it's false, then we would reject it. And those two decisions, again, have correct decisions and not correct decisions in the same spots as before. So if the null is true and we don't reject it, that's a correct decision. We would hope that that's what would actually happen if the null is true. Same thing as if the null is false, we want to reject it. Rejecting a false hypothesis is also a correct decision. And most of the time, we hope that we'll land in those two spots, just like with the jury. The other two spots are specific types of errors. And yes, you're going to need to know which type is which. So I'm going to start with if the null is true and we reject it, that is called a type 1 error. You need to remember that that's type 1. Type 1 error means the null is true, but we reject it, and we will come back to reasons why that would happen and how to avoid it down below. But for now, this is called a type 1 error. It's the equivalent of putting an innocent person to jail. We're falsely accusing this statement or this claim of being false when really it's true. All right, and then the other one is if the null is false, but we don't reject it. You probably could have guessed this is called a type 2 error. And yes, they usually use Roman numerals for that. Also bad. Also, just like with this, means we just don't have enough evidence to reject. We could maybe fix that by taking a bigger sample and getting more evidence, which we'll talk about that down below also. So both of these are things we're trying to avoid, but they sometimes happen even if we do everything right. So let's go into more detail about those two types of errors. Let's talk about type 1. Type 1, this is what you're going to work on memorizing, is when the null is true, but we reject it. Or in other words, we reject because we get a low p-value. We get a very small probability of something happening, but that could happen for a number of reasons. It could happen because the null is really false, but when we're making a type 1 error, here's what's happening. Why would this happen? Think about a normal curve. And we have this center value that is our parameter. We're saying the null is true. So this is really p or it's mu, depending on which type we're doing. And we get a p hat or x bar value that's further out away from that. Let's say it's way over here. P hat or x bar is over there. And because it's over there, we find this little piece of area, which is called the p-value, which is the area under that piece of the curve. And it's small, so we reject the null. That means basically, if we're saying the null is true, that means we got a rare sample. And you already know that that sometimes is going to happen. If you have this as your parameter, your sample value will come out most of the time close to this, but sometimes it comes out far away. And if it comes out far enough away, we would reject the null. As you know, this happens 5% of the time with our usual cutoff, even if we did everything right. So that significance level is the same as the probability of making a type 1 error. Probability of type 1 is usually 5%. It's called alpha, Greek letter, and it's the significance level. That significance level of 5%, or sometimes other than 5%, is the probability of making a type 1. And it's basically the only way to fix that problem is to reduce the alpha. How do we fix this? Or how do we reduce this probability? We reduce alpha. And sometimes that is done for that very reason, especially in court cases. Very often in court, they require evidence that's stronger than 5% to convict somebody. So maybe the evidence has to be 1% or less, because they really, really don't want to send an innocent person to jail. So if that's really important in the situation, then not do this or not do this, then you'd use a smaller alpha to avoid that problem. And that's basically the only thing you can do about it, because it's the same as the significance level. So type 1 is pretty straightforward. We already have seen that 5% thing. It's the same as the 5% of confidence intervals that don't capture the true proportion. Same basic idea. Let's talk about more details on type 2, which is actually a little bit harder to deal with. So the type 2 happens when H null or H naught. Sometimes they call it not, sometimes they call it null, H0. Anyway, if it's false, but we don't reject it, which means we got a higher p-value above our significance level, and that caused us to not reject. And in other words, we just didn't know that the null was false. Why would this happen? And I gave that to you up there. It basically happens when you don't have enough evidence. Like you think that you have evidence that says it's not true, but it's not strong enough evidence, not strong enough or not enough. And that generally happens when you have too small of a sample. So let's think about what happens with small samples. Small samples cause a large spread in the sampling distribution. Why would that make a difference? I'm about to draw you a picture of that. So, normal curve, no big surprise there. We have our hypothesized value in the middle. This time I'm not going to say that this is P or mu. I'm going to say that this is our null hypothesis. It's our hypothesized value of the parameter, which we use that value, the value from our null hypothesis, to do our calculations, which we haven't really done a whole lot of yet, but we will. We think this is true. That's nice. So we do our calculations based on that, and let's say we get a sample value that's over here somewhere, and it's not enough evidence to reject, so this is more than 5%, but maybe that sample value is over there because the real null hypothesis or the real parameter is here instead of here. So this is our statistic, p hat or x bar, and this might be the true value of P or mu. And if that true value is over here and the false value is over here, then we may get something in between that wouldn't cause us to reject. So I'm going to draw another normal curve centered around this value. And what's happening here is we calculate this little guy and it's bigger than 5%, but the chance of that happening is actually pretty large. So that's kind of weird. So basically what's happening is we calculate this value of the probability of being from here over, and it comes out bigger than 0.05. And so we don't have enough evidence. If we got something over here, then we would have rejected. But if we get something over here, then we're not going to reject. And maybe right there we would reject. So it's just like we're on the border somewhere. What's interesting here is there's two different normal curves. This is what we think is true. And this is what's really true. And how far apart these are makes a difference in how likely this is to happen. Where our sample happens to lie makes a difference. There's a lot of things that influence the probability of type 2 error. So I'm going to give you the easy part first, which is how to fix it. Or how to reduce the probability of a type 2 error. And to reduce it, I gave the hint up here where it's saying not enough evidence usually means too small of a sample. Because if you make your sample bigger, that would reduce the spread of this and it would make you more likely to reject. And that's what we want. So there's two ways to fix it actually. One way would be to increase your alpha value. And that would be saying, okay, well, maybe 5% would not reject, but maybe 10% would. Maybe this is a 10% right here. And I could reduce my chances. I'd be more likely to reject the null if I had a bigger alpha. The problem with that, this is not a good idea, by the way. The problem with that, although it's sometimes done, is it increases the probability of type 1. So you're sacrificing the innocent people in order to convict the guilty people more often. That's not so good. But a better way is what I told you up above. Not enough evidence means we just need a larger sample. Increase the sample size. And that has the advantage of fixing this problem without making this problem worse. So increasing the sample size reduces the spread. And I think I should draw that in a different color. So hang on while I get my red pen. I could reduce the spread of this so that and actually it would reduce the spread of this also because I'd be using that new calculation. It would make this little guy much less. So reducing the spread makes it so that the overlap between these two curves is not so much. So that's the best way to do it because it doesn't mess with the probability of type 1. Officially, the probability of type 2, as you might have guessed, or maybe you wouldn't, probability of type 1 is alpha. Probability of type 2 is called beta, which is another Greek letter. And we're not going to learn how to calculate beta. Beta is something I had to learn in graduate school how to calculate. And basically, I'm just going to say you can't do it unless you know a lot more than we usually know. You can't calculate beta unless you know the true value of the parameter, which we're saying that null is false, and so the true value is not the same as the null. So basically, there's a couple things that go into it. It has to do with how far apart these are, which you would have to know, and it has to do with the sample size and the alpha, and all of those things contribute to beta. We're not going to worry about that. That's not an AP Stats topic. It's an advanced college-level statistics topic that you'll learn if you take more stats. But let's talk about something good after all these errors. So we're not going to learn how to calculate this. I'm just telling you that it's called that. But let's talk about one more thing that's a good thing, and that is called the power of a test. So the power of a test is the good side. It's like, okay, let's say our null is false and we want to avoid a type 2 error. So that means we want to get into this category. We want to reject the null. We want to convict the guilty person. And that's the power of a test. How likely are we to actually do that? It is officially the probability of rejecting the null given that the null is false. So that's interesting. If the null is true and we reject it, that's type 1. If the null is false and we reject it, that's a correct decision. And it's the opposite of a type 2 error because we're saying given that we're in this column, the probability of rejecting would be the complement of given we're in this column, the probability of the wrong decision. So it is the complement of a type 2. It is 1 minus beta, which is 1 minus the probability of a type 2. So in other words, if you are trying to avoid type 2, that means you're trying to increase the power. Another way of saying this is it's the probability of correctly rejecting the null. And so to increase the power, which is the main thing you need to know is how to increase the power. You don't have to know how to calculate the power. Is the same as decreasing a type 2 error. And so the same thing I said up here, there's two ways to do it. You can increase the sample size, or you can increase alpha, which is your significance level. I'm going to put this in parentheses because it's not the best way. This is the best way because it doesn't mess with your type 1. So for the purposes of this class, you don't have to know the calculations part, but you do have to know how to increase the power. Basically, how if the null is false, you have more chances of rejecting it if you use a bigger sample size. Doesn't that sound familiar? Bigger sample size gives you more evidence, gives you better results, gives you more, it makes it more likely that you'd find the truth. So that's what today's lesson is about. And more on that later.